Hey everyone, welcome to lesson 6 or 7. I don't really remember. Um, so today we're doing the inverse matrix, but before we get into it, I'm just gonna, I think, be shifting my tactics a little bit of trying to intersperse just looking things up, uh, somewhat trying to repeat my process of thinking while I was doing this the first time myself, um, while doing it partially from memory, and instead of doing it almost completely from memory, but like showing things as it goes. I'm gonna try to do it from memory as well, mostly for myself, um, because it's better practice for me, honestly. But I'm gonna try and explain everything along the way and look up things and showcase things to you, and as I'm doing it, and try and just hopefully is put into you just the concept of through my questioning and thought process, like think about how you can think of that process applying to whatever you want to learn, because that's the main thing I really want to do with this channel, is have several series similar to this where it's not about like learning X subject, but it's like learning X subject as an example of learning how to learn, right? um, and I also don't want to devolve into those like, here's like 5 tips to make you study 24/7 without sleeping and 7 hour energies, or whatever. Yeah, I don't want to be one of those guys. I do want to actually put out value in the actual content itself and being able to learn directly the subject as well, but also always keep an eye towards, how you can apply the meta learning process to other places. So, with that said, let's just get into it. I'm not going to be showcasing my tabs because they get messy and it's really not a good reflection of how I am when I'm actually doing it. Um, so yeah, let's get into it. So we yesterday we came up to the cofactor matrix, right? Now the cofactor matrix is pretty straightforward. But just to review, I have this image that I had looked up. It's essentially, for any given matrix, every element is essentially -1 raised to the power of I plus j times the determinant of that minor, with reference to that element. That is what the cofactor matrix is. So basically, here, for example, for M11, you take -1 raised to the power of 1 plus 1, so -1 raised to the power of 2, so that's 2. Sorry, that's 1. Just +1 times the determinant of the minor, which would be the determinant of 3821 over here. See, as illustrated. Let's see if I can find a better one. Okay, okay, that's a super blurry image. Uh, oh, that was the same one I had. Oh, this is the one I remember looking at. Step 1, you take the minor over here. Step 2, you actually calculate the determinant of the minor. And then step 3 is -1, raise to the power of I plus j for that. And step 4, you do that for every element in the matrix, right? And that's how you get the cofactor matrix. Now, to go from the cofactor matrix actually to the inverse is pretty straightforward. Now, remember to calculate the inverse. The matrix needs to be non-singular, um, meaning that the determinant needs to be not zero, right? Which is why when calculating the determinant in the matrix, I am setting it to raise a value error that the matrix is singular and non-invertible. Now, another question you might ask if you were doing this on your own is what does it mean for determinant singular? Something like that, right? It doesn't need to be. Determinants are calculated for square matrices only. If the determinant of a matrix is 0, it's called a singular determinant. If it is 1, then it's known as unimodular. Oh, okay. Even I didn't know that. So, more we learn. Didn't know that was the term for it. For the system of equations to have a unique solution, the determinant of the matrix must be non-singular. That is its value must be non-zero. So that's why the determinant. Oh, there's a bug on my laptop. I'm gonna kill him. Kill the bug live, guys. Everyone. Unfortunately, not a software bug, but we did do that last episode, so that's fun. So, that's pretty great for system equations to have unique solutions. So now you know what the value of a determinant is rather than just knowing how to calculate it, right? That's like a question. You could have just heard those words I said about it being singular and non-singular and blah blah blah, right? And like, okay, maybe if you're not even aware of a linear system of equations, you could even just Google what is a system of equations, right? Like, in fact, we could do that right now. What is a system of equations, right? System of equations, set of two or more equations that share the same variables. Goal is to find values for variables that satisfy all equation systems simultaneously. Now you can explore this and whatever, and just whatever question comes to your mind. Be willing to go broad. At a certain point, you'll hit bedrock, and you know what? You might hit that bedrock of like, oh, we've gone so deep. Like now it's really talking about stuff that I actually don't understand completely, and it's gonna be a lot of effort to break through this. That's when you can like come back. Okay, it's like, okay, let's scroll back. This was the thing I was gonna do. I'm gonna go do that. Learn by doing. So start with a curiosity. You know, start with actually curiosity. Like especially when you're formulating a plan. Like when I created this, the thing was like I broadly wanted to study X subject, and so I formulated a plan where each step of learning from beginning all the way to the end is done in a way in some sort of working fashion where I'm actually using that knowledge in some way or recreating it or applying it in a certain way, right? Now for pure maths, you could have done this just by like creating a bunch of questions from ChatGPT or just buying a textbook or honestly, you know getting a PDF copy of a textbook through certain means online, and just doing the math questions yourselves. But for me, it was more valuable to do it in code. It might not be the valuable way to learn for you, at least starting off, right? Um, so whatever that appropriate marker is of doing the thing, you need to find that and do that. That's the best thing. And like, you know what? Give yourselves the space to think about things. When you're thinking about, when you stop in between like reading a sentence, you start thinking about it, and give yourself also the space to not think. Both are valuable. Like if you're getting stuck, or if you're not able to process, or even if both of those are going fine and you just like happen to drift off for a moment, allow yourself to drift off. That's okay. Your brain will consolidate things slowly. Brain consolidates things after rest really well, right? So make sure to allow your brain the space to do that and come back to things slowly over time. That's how things really cement. That's part of why I'm doing this. It helps me review, and it's another learning technique, because one of the best ways to learn is to teach. And honestly, the best place to end up is teaching in a manner that is simple for someone else to understand. That's when they say mastery is achieved. Though I don't think I'm very good at explaining things in simple terms. So just getting got a little lost in the cofactor of a matrix, right? So we're trying to find the inverse of a matrix, right? And that was me explaining why the determinant has to be non-zero. Well, actually, I don't think we actually Googled that. We could Google that too. Why does determinant have to be non-zero for a matrix to have a unique solution? Let's see if there's a matrix must have not. This is because non-zero indicates that the matrix is invertible, allowing for a unique solution to be found by multiplying both sides of the equation by the inverse matrix. Oh, okay. Some more detailed explanation. Invertible matrix. Okay. It has an inverse matrix for a system of equations represented as ax equals b, where oh, there's another bug here that I just killed. Where a is the matrix, x is the vector of unknowns, and b is a constant vector. Multiplying both sides by the inverse of a gives x equals a inverse b. This provides a single unique solution for x. Huh. Okay. I actually did not know this. Oh my god, this is awesome. I'm gonna start doing this always from next time rather than showing you guys my tabs. This is way more fun. Huh, we're all having fun. My wife's on the couch. She's super bored. She's tired of my nonsense. She's. Is she even listening to me? I'm not sure. I'm walking. Oh, she's working. She's awesome. I love her. She's the love of my life. Anyways, now she's smiling. I got her to smile. Yeah, you gotta keep him smiling, boys. For any of you at home. Well, I mean, that's not necessarily true. This is not a relationship channel. I'm not going to give you relationship advice. Let's continue. Okay, so that was a great question. That was great. Like, this is what I mean. Like, you can do that in the middle of this, and this is me coming back to something that I've already done, actually. And there's always more to explore. So, anyways, so we can get the cofactor matrix like so. Cofactor mat. We don't even need to do that. We can just call that co. Actually, I think the adjoint matrix. So we're just gonna Google that again, but I recall very clearly that the adjoint matrix is the transpose of the cofactor matrix, and it is. So I'm just gonna do that. Transpose cofactor matrix, right? So let's just call that ADJ. That's the adjoint, right? And we'll go, and we have to multiply each item in the matrix mat with 1 over the determinant, right? Yeah. And then we have to actually okay, yeah, so we got 1 over determinant times the ADJ matrix, right? The adjugate, there you go, that's the word. Crucial concept, okay. 1 over determinant. Let's just confirm. I remember very clearly that the inverse of a matrix, I think it was in method 2 over here. Yeah, it's adjoint can be found using the following method. Yeah, inverse is just essentially 1 over determinant times the adjoint, or adjoint over determinant, however you want to define it. And so I want to do m times e for e in v for v in ADJ, and I believe we just returned that. I think that is the end there. So look up let's read what this is about with the inverse matrix. In simpler terms, to find the adjoint of a matrix, calculate the finding the inverse. The adjoint is directly related to the inverse of a matrix if A is invertible. Its inverse can be calculated using the adjoint and the determinant. Adjoints used in Cramer's rule, which is a method for solving systems of linear equations. What is Cramer's rule? I don't know what Cramer's rule is. It's a method for solving systems of linear equations using determinants. It's particularly, let me see if I can do this. A1x plus b1y, a1 b1 e to b2 equals d. Y equals dx. What is dx? C1 b1 c2 b2 c1 b1 c2 b2 over d, and y is dy. Oh, I see. So I guess this derives from the fact that you could rewrite the equation in different ways to be with respect to different variables, right? I'm guessing. It's pretty useful when you have the same number of equations as unknowns and the system has a unique solution. The rule involves calculating the determinant of the coefficient matrix. Oh, so these are determinants, that makes sense. And determinants of modified matrices where columns are replaced by the constant terms. Rule involves calculating the determinant of the coefficient matrix and determinants of modified matrices where columns are replaced by the modified matrices and columns are replaced by the constant terms. Columns are replaced by the constant terms. So yeah, I guess that makes sense. Yeah, it's in writing what this is showing, so that makes sense. Consider a system of linear equations where A is good. Okay. System AX equals B. So AX equals B, I'm just gonna like hum over that. But AX equals B, whenever you're saying that, you're saying the matrix A times the vector X, so equals B. So if you have like X plus 2Y equals 10 and X plus 3Y equals 12, for example, you can do that as 1, 2, 1, 3 is one matrix, and then the vector X is just X, so X and Y, and then B would be 10 and 12. So that's just a common way of representing a basic system of equations, and what you're actually trying to solve for is that vector X, right? Determinant of A, calculate the determinant of coefficient matrix, modifying for each variable unknown, create a new matrix by replacing the corresponding column in A with constant vector B. For example, if you want to solve for x1, replace the first column. Okay, I don't want to go too deep into this, but I'm just gonna save this tab, and maybe we'll come back to Kramer's rule later. But this was fun. I'm definitely gonna. This is actually, I think, a much better method of doing this and showcasing what I was trying to show rather than just going through my tabs. Let me copy some asserts really quickly from when I did this earlier, which was here. And we will confirm that this is working. Oh. Command A, Command V. Oh, not Command A, Command C. Yeah, gotta do Command C after Command A. Okay, let's get a few more going. Let's see, what else is there? I think we got some over here. Actually, I'm just gonna drop these prints. Let's just run these. Ooh. What is the problem here? The adjoint is the transpose of the cofactor matrix. Assert all. Well, let's see what the actual answer is. Let's just break this up a little bit. Issues coming in over here, right? So let's just print that. And B underscore A. You okay, babe? Okay, 0.6001 negative 0.2 negative 0.7.4. This is the inverse of okay. Well, let's just look up a inverse calculator, because this could have been an issue when we generated this and that I somehow missed, because the matrix dimensions are 2, yes, set matrix. It's 4, 7, 2, 6. Calculate 3/5. Okay, 0.6 is 3/5, yes. negative 7/10, negative 1/5, 0.4 2/5. Yeah, okay, so this is correct. This is the mistake, but how? Where have I got this wrong? I don't think it's where I'm getting the minor, otherwise I wouldn't have gotten the shape right. There would have been an issue there. Determinants we know is working fine, so it must be something with the cofactors. No, we calculated the cofactors appropriately, because I recall us. Okay, yeah, let's just double check this. Yeah, I'll call all the cofactor tests pass. We did that in the last video. Okay. Well, that's obviously not working because the answer here is negative 0.2, but why is that happening? Did I somehow forget how we do the inverse? No, it's the adjoint of A divided by the determinant of A. Let's take a look at what we did earlier. No, it's the exact same. Oh, that's right. I made the mistake. Wait a second, no. This doesn't make sense actually. Did I make a mistake on how we do cofactor matrices? Let's see. Huh. 1 over the determinant AD minus BC times dA by MB minus C. I think I've been putting into the cofactor matrix. What the adjoint is. Cofactor matrix of a 2 by 2 matrix. Is that the mistake? Just gonna look this up. Oh, that was not helpful. There's some as well. It's D negative. And the transpose of this would be D negative C. Oh, okay, I made a mistake that somehow worked yesterday. I don't know how, but it did. Somehow we passed all our cofactor tests. Let's just confirm this adjoint of a 2 by 2 matrix. D negative B negative C A. Yeah, D negative B negative C A. So what we have here is actually not the transpose. This bit of code here is actually the adjoint of a 2 by 2, not the cofactor of a 2 by 2, which is why I'm getting screwed up here. But what I'm trying to understand is, how did that work for this? One, two, three, four. look at the images to make sure I'm not losing my mind over here. This is not that helpful, honestly. Okay, let's go to T2, which is complaining that I have ad block on. And with how much crap it's thrown at me, I'm very glad I do. This is a very poorly designed website. Let's just look at what Byju's has to say about that. Okay. Let's visit QMath because I remember having come here earlier. All the examples it gives us of cofactor matrices of 3x3s, that's in the explanations, but there's an example here. Represents a 2x2 matrix for matrix A, B, C, D. Is D negative C negative B A? Oh, okay. Hence the cofactor matrix of the given matrix is. Okay. That means ChatGPT screwed us yesterday and just gave us cofactor matrices that are actually adjoints. That's what they've done here. That's so much for trusting ChatGPT, right? Gotta be careful. Gotta be careful, guys. Okay, so A, B, C, D becomes D negative C. So this actually becomes 1, 0, negative B. So that becomes 0, 1. And then, yeah, okay. Now let's test this. And we're good. All right, cool. These will start failing now because these are wrong. Okay. So, yeah, and that's, I only caught this because I did it differently here than how I did it earlier. Because earlier I just had the regular cofactor matrix, and then since I never called cofactor matrix separately and I only called adjoint, and I had the logic right for adjoint, and I just kind of blindly threw it into cofactor, and we also got lucky with ChatGPT just spewing out some nonsense. I gotta be careful about that. Anyways, that's the video, guys. We got to the end. I thought this was going to be a really short one. It should have been, honestly, by all rights, but this was way more fun for me. I learned a lot more, and I feel like I think I did a better job of showcasing, you know, that all questions are valid. You should always ask all of them, you know. Some of them are like maybe a bit too simple for me, like asking what a system of equations are, but maybe it's not for you, and you should be totally willing to go down that rabbit hole. Remember, everything else is tips and tricks and all that jazz, but the thing that sparks it all is curiosity. Thank you guys for watching me. Have a great one.